going to take a look at the greatest common divisor and the least common multiple. And I want to talk first a little bit about the language that's used on these, because it is easy with English for it to get confusing. But I want you to understand that the word greatest and the word least here do not mean greatest means it's the biggest and least means it's the smallest. They're adjectives. So I do know some English. These are adjectives that are describing the noun that comes after them. Okay, so the word greatest is an adjective describing the common divisor. But divisors are typically small numbers, so it's the biggest small thing. I mean, that's what it really is. Okay, so the greatest common divisor is typically a small number. And then a least common multiple, again, least is an adjective describing common multiple, but common multiples, or multiples in general, are bigger than what you start with. So your least common multiple is typically a large number. All right? So try to keep straight in your mind that really greatest common divisors are usually smaller than least common multiples. In fact, almost always. So we're going to actually try to get done with the greatest common divisor part today and then do the least common multiple part next time. That's how I usually break this up. All right, so a greatest common divisor, or it's sometimes called a greatest common factor, is the greatest whole number that divides all the numbers in your set of numbers or group of numbers. So the words relatively prime were probably on one of the videos that you guys watched in 4.1 or 4.2. If not the words, at least the idea behind them was. There's an activity that I usually do when I teach 4.1 and 4.2 where we stop and we say, what is it that makes something work? And it's this idea of them being relatively prime. So you may have seen this before. Relatively prime is two numbers whose greatest common divisor is 1. In other words, they have nothing besides the number 1 that divides both of them. It doesn't actually mean that either of the numbers themselves have to be prime. For example, the numbers 4 and 9 are not prime, right? 4 is divisible by 2, 9 is divisible by 3. Those are not prime numbers. However, they are relatively prime because they do not divide by any number in common except for the number 1. Okay, so try to keep those phrases a little bit distinct because they sound funny. They're not prime numbers, they are relatively prime or prime to one another. We're going to learn several methods for finding greatest common divisors. And I think that this is very interesting because depending on when you teach children about this concept will depend on which one of these methods makes the most sense for a child at that level. Now, if you did this method that I'm about to teach you and you did it in middle school, the kids would probably look at you like that is the dumbest thing ever because it's time consuming in general to do this process. But if you're working with small numbers, which you would be if you were first encountering this topic in an elementary school, this process is a very nice process and it works it's very intuitive about what you're doing. And so that part of it's really nice. So the intersection of sets method has you list out all of the values that are divisors of the numbers you're working with. And then find the one that's the biggest in both or all three or whatever lists. So you're making a bunch of lists and you're looking for the biggest thing in both lists. And I say the word both because usually we're comparing two numbers. We don't have to be, but you usually are. So for example, 12 and 15. So the greatest common, or the intersection of sets method says, we're going to write down all of the divisors of 12. Not primes, not anything, just all of them. So the first divisor is 1. You'll always start with 1. So you're always going to have the number 1 and the number itself in your list. What is the next smallest thing that divides 12? 2. And then what? 3. And then 4. And then 6. And finally 12. Another thing you could do is you could actually list them in pairs. If you'll notice, 1 and 12 go together, right? 2 and 6 and 3 and 4. So they do always occur in pairs. Occasionally the pair is the number with itself. Think about like 16 is 4 times 4. So that sort of doesn't look like a pair, but it is, okay? So you could list them out in pairs or at least list them out sort of in this rainbow approach where you're listing them, towards you until you get to the middle where they meet. The other one is 15. So we'll start with 1. So if I think about it like I just said, I could put 1 and 15. And then what? 3 and 5. And actually that's it for this one. And you're looking at these two lists of numbers and you're saying, what's the biggest number that both lists have? And that answer would be 3. So the greatest common divisor is 3. Okay, so for the numbers 12 and 15, this is not especially, time-consuming. It's just not. But if you had a larger number than, say, 12 or 15 that had lots and lots of factors, this is kind of messy, right? Okay, so there's always pros and cons anytime we're working with different methods in mathematics, and that would be the con for this one. But in terms of small numbers, this is a very realistic approach. All right, this next one is probably the one that you remember. I'm thinking this is about 6th grade, maybe 7th grade math when you first see this. It's called prime factorization method. And you usually start, the place where you use this is actually a viable piece of information, pretty important, is because always kids want to know, like, when am I going to use this in real life? You know what I'm talking about, right? In fact, I'm pretty sure that about half of you have at least thought that at some point when I've said something in class. I'm sure you have. But what this is used for, maybe not real life in that sense, but at least in further mathematics, is being able to add and subtract fractions. You need to know what their divisors break down into in order to find a common denominator and to add fractions together. That's a very practical, pretty quick place where you have to be able to use this information. All right, and prime factorization is often how people think of this one. So what we do is we construct the prime factorization of each number, which you know how to do, because that's what happened in section 4.2. I said 4, did you notice that? 4.2, I know, it's great. And the second thing you do is you look at what prime factors that the two numbers have that are in common. Okay? Common. And then you look at the exponents that they have. So maybe both of them have a 2 in them, but one of them has 2 cubed and the other one has 2 squared. Okay? So you look at the exponents, the squared and the cubed, and you pick the smallest exponent, and you use the smallest exponent, and then you find the product of all the numbers. That's what you do at the end. And as always, this works better if I actually show you an example. Agreed? Yeah, for sure. All right, so here are our numbers, 400 and 360, and raise your hand if you're glad we aren't doing the sets method from before with these numbers. Yeah, that's me, because these are pretty big numbers to try to do that with. Okay, but they work really well to do prime factorization method. So you're going to take whichever number you want first. I'll use 400 just because it's first. You're welcome to a factor tree if you'd like. I tend to not like factor trees as much, which I probably said in the video when you guys watched it, because the other method keeps them in order from smallest to greatest, and I don't accidentally lose the end of a tree branch somewhere along the way because my work kind of got big and scattered. So what I do is I would look at this and I would find the smallest prime number. It did say prime factorization, so you do need primes to do this for this particular part. Prime number that goes into 400, and that would be the number 2. And I divide. And then I can divide by 2 again. And again. One more time to give me 25. Doesn't divide by 2, doesn't divide by 3, does divide by 5. And I'm done because 5 that I just ended up with at the end is a prime factor. So I've got 2's and 5's. How many 2's are there in this list? 4. So this is 2 to the 4th. And how many 5's are there? 2. So this is what you would have done back in section 4.2. Agreed? Okay, so this should not look new. If you watched the video, if you did the homework, this is what you did. Now, the other number was 360. So we're going to do it same way again. Again, if you want to do factor trees, you can. I'm not going to be like mad at you for doing factor trees, but I'm going to do them with this division method. It needs a name. Did I give it a name in my last semester what did I do? I need a name. Somebody needs to have a name for this for me because I've never seen a name for this method of division. Maybe I should offer extra credit. I'm not going to. But I should because I need a name. Okay, this divides by 2. Back on track. 360 divided by 2 is 180. Very good. Which divides by 2 to give me 90, which divides by 2 to give me 45. Don't go stretching it into 5's yet because it actually divides by 3 first. What's 45 divided by 3? 15, which also divides by 3, and then I have a 5. Okay, so I've got 2's, 3's, and 5's. How many 2's? 3. How many 3's? And how many 5's? And I'm going to go ahead and write the 1 as the exponent just so that I see it there visually when I'm comparing. It makes it easier for me anyway. Okay, so basically what we've done now is step number 1. We've constructed the prime factorization for both numbers. The next thing we're going to do is we're going to figure out what prime factors they have in common. So I've got 2's 5, 2, 3, 5. What do they have in common? 2 and 5. Now occasionally I have somebody who will stop here. Not occasionally. Almost every semester I have about 2 or 3 people who stop here. But you need numbers as exponents on there. Okay? It doesn't always, stop with the 2 and the 5. You have to go back to where the 2's are located. One of them has 2 to the 4th and the other one has 2 cubed. I need to use the smaller exponent of those two, which would be the number 3, the cubed, exactly. Because what this really says is that there are actually 3 prime factors of 2 in both lists. And I want to list them all. Now there's no 3 in the first list, so I'm not using it, but there are 5s. How many 5s? Just one. And if you see that one, it's say right here. Okay, the last thing then, well, that's actually 2 and 3. We did those. 4 says to find the product of the values from number 3. So what is 2 cubed? 8, and 8 times 5 is 40. So the greatest common divisor, or greatest common factor, those are the same thing, is 40. Who has used this method before? Something like this. You haven't? Catherine has. Beth has. Okay. It is a pretty common method. Probably of the 3 or of the 4 methods I'm going to show you, this is the most common. At least when you get to numbers that are large. The first method's fine, but when you get to large numbers, this one tends to be the most common. This one's actually my favorite. I like this method a lot. This is called division by primes. What we're going to do is we're going to write the numbers in a row. We're going to divide each number by a common prime factor. And then we're going to repeat. You know, like on the shampoo bottle where it says rinse, wash, repeat, or wash, rinse, repeat, whatever. We're going to do that. We're going to repeat that process until we have no other common factors. And then the GCD is the product of primes. It feels a little bit like what we're doing with the other method, but it actually is a quicker way to do it, which is why I like it. Quicker is good, right? It is, yeah. Okay, does everybody have these blanks filled in? I don't want to... You're still working, Caitlin? Okay. $410 and $360. Big numbers, right? Okay, the first thing we're going to do is we're going to write them down sort of beside each other. And instead of dividing each one of them out into all of their primes, we are only going to divide them by the primes they have in common. And we're going to start with the smallest one again because it's usually the simplest place to start. What's the smallest prime number that divides both of these numbers? 2. What is 410 divided by 2? 205. And then 360 divided by 2? 180. And it just occurs to me, does anybody have any test redos they want to turn in? Not yet? Okay. Somebody was gone last time. I have your test in my binder to make sure I get it. Okay. Sorry, moment of distraction. They're not both divisible by 2 anymore though, right? No. So we go up the chain of command of primes. 3. No. 5? Yes, they will both divide by 5. Okay, so now we're going to divide by 5. What is 205 divided by 5? 41. And 180 divided by 5? 36. Okay, so we already tested 2's and 3's, now 5's. Do they divide again by 5? No. 7? No. And I expect, hopefully at this point, can't remember if it was already in 4.1 and 4.2, I feel like it was, that you know that you can stop at 7. Does anybody know why you should be able to stop at 7 here? Right, because the square root of 36 is 6. So there was a property that we had, was it in the video? I'm not imagining that, right, Beth? Okay, there was a property in there that said you can stop testing for divisibility by primes once you get to the square root of the value itself, and 36's square root is 6, which is smaller than the 7 I just suggested. So I don't need to test anything beyond 7, which means these don't have any other prime factors in common. And in fact, 41's itself a prime number. You may not know that. It's kind of a large prime number compared to what the lists are that you learn, but it is prime. So we stop at this point. The answer for the GCD is everything you divided by multiplied together. So the reason I like this idea is because on this problem, if I had done this the other method, the last one I just did, you'd have to keep going with 36. You'd divide 36 until it was completely all done into its primes. And you don't really need that information, do you? You don't. That information is completely irrelevant to this particular question. The part you really only needed was the part that primes that divide both the numbers. And so this actually gets to the heart of the issue much quicker. And there's one other method that you probably haven't seen ever. Maybe you didn't the last one either, but this one's quite unusual. This is the Euclidean algorithm. And for what it's worth, I have seen questions related to this particular algorithm on different tests. Not the one that I just worked on. Remember I told you I was helping to do the state test for the middle grades licensure. This was like about 6 or 7 years ago where they had a question related to the Euclidean algorithm on that test. All right, so the Euclidean algorithm, what you do is you divide the larger number by the smaller one. You take the previous divisor and the remainder, and you repeat that step until you get a remainder of 0. The last divisor is the greatest common divisor. And I know I said that really quick, and the reason I did is because this one makes no sense until I show you an example like 0 at all. Not even sort of, kind of. We might get further today than I thought we were. That's okay. That's not good. That's great. That's good news. That means you'll have more time to do group work next time. That's what that means. Okay, 72 and 126. So what you're going to do is you're going to divide the bigger number by the smaller number. So 72 on the outside, 126 on the underneath of the division. And you're going to grab your calculator if you need to. On this one, it's not a terribly difficult one to just do in your head. It only goes in one time. And you're going to find the remainder. What is 126 minus 76? Oh, wait, I'm sorry, 72. I was looking at my numbers wrong. 72.
54.
54. Okay, what you do at this point in the problem is you take the previous divisor and the remainder, and you do it again. Okay, whichever one's bigger, which it should be the divisor, otherwise you didn't do the division right here right, goes underneath. And the remainder goes on the outside, and we divide. How many times will 54 go into 72? 1. And the answer is not always 1 here. It just happens to be this time. So it's 54. What do you get as a remainder here? 18. And we do it again. We take the 54 and the 18, and we put the 54 underneath. The 18 on the outside. How many times will 18 go into 54? More. Yeah. It'll go in 3 times. Figure out, what is 18 times 3? It's 54, yeah. And that's the remainder of 0 that we're looking for, right? This is when we know we're done. Once we're at the point where the remainder is 0, what that means is it means that the last thing that we divided by, in this case, whoops, the 18 is the greatest common divisor. It's not a super hard process, but it is a little bit more hidden as to what's happening in the problem to actually get to the point where you're getting the right solution. It's not very obvious like the other ones were. Okay, let's move on into least common multiple because we've got time. The least common multiple is the least non-zero whole number that is a multiple of all whole numbers in your set. When I think of least common multiple, I think of my multiplication tables. So who did multiplication tables in something like 2nd or 3rd grade? I did. we had these tables, and what we did is we memorized lists of numbers. That's how we started anyway. And then we did flashcards and so forth from there. But it was lists of numbers first. It was 3, 6, 9, 12, 15, 18. I mean, like that, not 15. That was, it was. I was right, 15, 18, yeah. We did it for 4s, and we did it for the 5s, and we did it for the 6s. And for whatever reason, when my daughter was doing it, they went to the 12s. I don't know why somebody decided going to the 12s was necessary, but they did. And so they had these multiple lists, okay? Well, that's what the idea is for least common multiples, is you've got lots of multiples and you're finding the smallest one or the first one that they have in common in some kind of an argument. And in fact, that's our first method, is a list. So this is the number line method, or colored rods. So it has 2 names. I'll explain why in a second. Sorry, the second method was the one I was just about to describe to you. I totally almost forgot this one. So the number line method shows multiples of all numbers on a number line in the intervals of each value. And the first value at which the intervals coincide is the least common multiple. So there's some wonderful pictures in your book. I should probably put them inside of this presentation just so that you can see them, but I'll draw my best at doing them instead, and you'll be okay with it, I'm sure. Number lines, which you can create at any point you want, is what one of these methods sort of describes this as. The other one, where it says colored rods in parentheses, is because there are actually math manipulatives that are colored rods. Does anybody know what I'm talking about? Have you seen them before? No? Okay. There was I can't remember what grade, I think it was a 5th grade class that had a set of them that I was in one time. So what they are is they're like Lego blocks, but they're not Legos, they're wooden, okay? And the wooden lengths are different. So like a red length is the same for every red wooden rod. So all red wooden rods are like 5 long, and all blue wooden rods are like 3 long, or whatever. And so the lengths themselves can just be stacked end to end, just like you would on a number line. You go 3, 3, 3, 3, they're all along, and at the point when the lengths match up, that's where you actually end up with a common multiple. So I'm going to draw a picture because I still see stares at me like I'm talking in a foreign language, which is okay. I probably am. So the idea is by putting them end to end, like this. I'm going to use red and blue since I mentioned red and blue. And they should be the same length. That at some point they will correspond to the ending value. They'll end at the same point in time, and that's where your least common multiple you would arrive at it. And so it takes 3 red rods and 4 blue rods to actually give you the same value. So let's do an example with numbers and the number line method, and I'll show you what the rods would look like that go along with it. So if you're doing the LCM, the least common multiple of 6 and 15 with colored rods or number line method, let me do the number line out, and then I'll draw the colored rods to show you what it would look like with that manipulative. So for a number line, you'd start at 0, and if you're going by 6s, you'd go from 6 to what? To 12, and then 18, and then my picture's going to be too small. Okay, I got to make it tighter. I don't have enough space. Let's try again. 6, 12, 18, what's next? 24, and then 30, and I'm going to stop there because you probably know at the point that this is where you need to be, and if you stop too soon, you'll know very quickly anyway. So the idea is that you're sort of skip counting by 6s, right, along your number line. And then the other value was 15, and so if you skip count by 15s, the first place you'd be stopping is at 15, which is right here. But then after you stop at 15, where do you stop? 30. So this right here would be our least common multiple. Okay. And from a colored rods perspective, it would look something like this. You have rods of length 6 end to end, drawn much better than I'm drawing them because, you guys draw better than I draw. I'm sure of it. Okay, so there's my rods end to end, or at least nearly so. And then here's my 15 rods. And if I've drawn them well, which obviously I haven't, but we can pretend like I did, they would end at the same spot, which represent the number 30. Okay? And your book does better pictures of those, of course, than I do. But this is the colored rods. This is great for your, what kind of learners? Kinesthetic learners, the hands-on people. People want to touch and feel things, who learn by touching. And so this is a really good activity. Again, it's nice if the numbers actually show up pretty quickly. But if we had done, for instance, 6 and 17, that would have taken a while, like a really, really long while, and it becomes a little bit less accessible. So you almost have to contrive the values for which this is useful, but that's how things are a lot of times in math, actually, is that you want the answer to look like, say, a whole number. Well, that means you have to make the problem start out in something that gives you a whole number as an answer, right? So that's not really necessarily a bad thing, it's just a reality kind of thing. All right, this method right here, a little bit less hands-on, but it still works very nicely for wanting to write out lists of multiples, which is kind of what happened on the last problem, but just in a visual standpoint. What you do is you list, it says all multiples, which is totally not true. So take this word all and mark it out and write a bunch. I know that's so specific, but just pretend for a moment. A bunch. You're going to list a bunch of multiples of each value because it's not possible to list all the multiples, right? Yeah, you can't do that because there's always one bigger. There's always lots bigger than the one you just said. And then you find the least value on the list. That is the first value that they have in common. So it's the smallest value they have in common instead of the biggest. So here's an example. We've got 12 and 15. Now, in the last time we listed things, we listed divisors, but here we're going to list multiples. So the first multiple on the list of multiples is the number 12. It's 12 times 1. This is where it looks like your multiplication table list. I didn't learn my 12s. Maybe you guys did. You can help me out. What comes after 12 in the 12s tables? 24. And then 36. 48. 60. And just for fun, let's list two more. 84, and then the next one would be 96. I'll stop there. That's good. Okay. And sometimes, depending on the numbers, you'll know kind of where you need to stop, and sometimes it's just a guess. You're going to list a bunch of them out on both lists and see if you hit. See if it actually hits the same, and if it doesn't, you list some more out. Okay? So there's not a real definitive, like, I know when to stop thing all the time. The other number was 15, so the first number on the list, of course, is 15. What's next?
30.
And then? And then?
60.
And let's list two more out just for fun. 90. Okay. And do they hit? Is there a location where they've already got in common a number? There is. It's the number 60. So the least common multiple of 12 and 15 is 60. Let me show you one other thing too. I keep writing this down as LCM equals, which is fine. There's nothing wrong with that. There are times when your book is very clear and it will write LCM like this, 12, 15 equals 60, and it's just specifying in its language that it's the least common multiple of the 12 and the 15. So if you see that, it's not saying like you're supposed to be multiplying or anything like that. It's just trying to further clarify least common multiple of what. Okay? We're going to use that fact, actually, that notation here in a minute. All right, next method is called prime factorization method. I flipped my page too soon. Okay, this is just the same as the title of one of the other methods for common divisors, right? Yeah, prime factorization. And it works the same way. You find the prime factorization, you figure out things about what they have in common, and in this case also what they don't have in common, and you look at their exponents, but you choose differently when you're doing it for least common multiples. So let me show you what it looks like for the least common multiple method. The example that I'm going to do actually uses 3 numbers. There's nothing special about that, but I just wanted to show you that you don't necessarily only have to have 2 numbers for any of these methods to work. So I'm doing an example with 3. So we're going to take the numbers one at a time, and we're going to find their prime factorization. So 90's smallest number it divides by is a 2. 90 divided by 2 is 45. Smallest prime factor that divides 45? 3. 45 divided by 3 is 15. 15 divides by 3 and ends me with 5. And the net result of all of this is 2 times 3 squared times 5. Again, that's from 4.2. Is that part okay?
Yes.
All right, good. The next number is 50. Smallest prime factor, 2, which gives me a 25, and then 5 and 5. So this is actually 2 times 5 squared. Last number is 20, which divides by 2 to give me 10, which divides by to give me 5. And so this one is 2 squared times 5. Okay, so what we did when we were doing greatest common divisors is we said, what divisors do they have in common? Right? What are the prime numbers that are the bases that they have in common? When we're doing least common multiple, we don't care if they're in common or not. We're going to list everything. We get all of it. This is kind of like that unions, intersections kind of stuff, right? Intersections is what do they have in common, and unions is like when you get married and you get all that and they get all your that, and you're like, oh my goodness, that's a lot of that, right? Yeah, this is it. You're going to get a lot of stuff when you do least common multiple. So for least common multiple, I need all prime factors. So what is the smallest prime factor in any list? 2. We'll worry about the exponents in a minute. What's the next smallest prime factor in any list? 3. Next one? 5. And I think that's it, right? 2s, 3s, and 5s. Now looking at the factors that have the 2 in them, I'll circle them all in purple. What I want is I want the one that's the biggest. Squared. The first one's squared. No, the first one's single, the second one's single, and the last one's squared. The biggest one then is a squared. Okay, we're going to do the same thing with the 3s. List all the 3s. Oh, there's just one of them. That's not very exciting. So what's the biggest exponent on the one that I have? It's a squared, yeah. Okay? And then we're going to do the same thing with the 5s. So we've got our 5s. What is the biggest exponent on any of the 5s? Happens to be squared. And so please don't think that the answers are always squared. That doesn't work. It just happens to be on this particular problem. You use whatever the largest exponent is. And then you're going to do just like you did with greatest common divisor. You're going to multiply it all out. 2 squared is 4, 3 squared is 9, and 5 squared is 25. So what is 4 times 9 times 25? 900. It is 900, that's right. So the least common multiple is 900. Told you you're going to get a lot of stuff, right? Yeah. Again, if you actually had to list out all of the I didn't say it again. Multiples, that's what I'm doing. If I listed out all of the multiples of 20 until I got to 900, my list would be long, very, very long, right? So that would not be an especially efficient way to do this problem. Doable, yes. Efficient, no. Okay? So prime factorization does work pretty nicely for this one. All right. Let's do division by primes, and then that will be, I think, maybe our last one. Division by primes works very much the same way as division by primes for GCDs. All right, you're going to put them in a list, and you're going to divide things. The catch is this. You can do a list of more than 2 items. So I'm going to do one this time where I divide by, I'm looking at a GCD or an LCM of 3 numbers. But when you're looking at the LCMs of the numbers, you want a divisor that will divide anything in 2 or more of the numbers. And I'll show you what I mean because my example has this happen. But you're going to be doing the divisors just like before. The answer at the end, however, is the product of all the numbers that divided it over on the side and the remainder numbers on the bottom, which we didn't have that when we did the GCDs. We just did the numbers that divided on the side. Okay, let's do an example. Told you I had one with 3 numbers. So you're going to write these guys sort of side by side. 90, 100, 20. And you're divide them by primes that they have in common. So what is the smallest prime that's common to these numbers? 2. So I have 90 divided by 2, so I get 45. 100 divided by 2 is 50. 20 divided by 2 is 10. All right, now do they have 2's still in common with all the numbers? No. How about 3's with all the numbers? How about 5's with all the numbers? Yes, so we'll divide by 5. So it gives me 9, 10, and 2. At this point, 9, 10, and 2 do not have something common to all the numbers, correct? They don't. But is there at least a common value among any of the numbers that still remain? The 2 and the 10 still have something in common, correct? 2 and 10 have what in common? 2. So you might look at this and say, okay, but what about the 9? And this looks a little bit funny. I totally agree with you, but you just rewrite it. You kind of ignore the fact that it doesn't have anything in common with the 2. That's not a very satisfying answer, I'm sorry, but that's what you do. The other 2 you do divide. So this one would give you 5 and this one would give you 1. And at this point, 9, 5, and 1 don't have anything except 1, obviously in common. The cool thing about this is that your answer is just the product of everything here. So the least common multiple is 2 times 5 times 2 times 9 times 5 times 1. And what do you get if you multiply all of those together? I think it's bigger. 900. That's okay. So mine's showing bigger than that, yeah. 900's right. Okay. I really like division by primes because I like that the answer's just right there. I think it's cool. Okay. All right. The last thing that we'll do in this section, besides some example problems, just to give you a heads up, is a relationship between the GCD and the LCM and how those correspond to one another.